Thank you kindly, Dr. Pierce. Our next keynote speaker, ladies and gentlemen, is Professor Makoto Tsubokura, who is a professor in Kobe University and a team leader at Riken Center for Computational Science. Now, he has been involved in development of CFD software for industrial applications for these 15 years. He is also part of the 6-member team who received the 2021 ACM Gordon Bell Special Prize for High-Performance Computing based COVID-19 research. Now, do join me, ladies and gentlemen, in welcoming Professor Subokura, who will be delivering his keynote speech virtually on digital transformation of manufacturing process and smart design in the Society 5.0 era, realized on the supercomputer Fugaku. Ladies and gentlemen, here is Professor Subokura.
Okay, thank you very much for the introductions and good morning, everyone. First of all, I would like to express my deep gratitude to the organizing committees for giving this opportunity of talking at this wonderful conference. I'm Makoto Tsubokura from Riken. Today, I would like to talk about digital transformations of the manufacturing process and smart design to be realized near future in industrial world on the supercomputer Fugaku. Here, I'd like to note that I would focus on computational fluid dynamics, or so-called CFD only, among various types of engineering simulations in this talk. To begin with, I'd like to introduce the concept of a future called Society 5.0, following the hunting, agriculture, industry, and information societies. This concept is advocated by Japanese government as a future society that Japan should aspire to. It is a society balancing economic advancement with the resolutions of social problems by a system that highly integrates a cyber and physical space. Currently, we are now in information society where we access cloud service or databases in cyberspace via the internet and search for, retrieve, and analyze information or data by ourselves. In Society 5.0, on the other hand, a huge amount of information from sensors in physical space is accumulated in cyberspace, and this big data is analyzed by AI, and the analysis results are fed back to us in physical space in various forms. In our team at Riken, we are seeking for new digital engineering to be realized in this Society 5.0. There, cyberspace below is integratedly combined to physical space above, where industrial design and manufacturing actually take place. There are some examples we are now trying to develop on the Fugaku platform with tight collaborations with automotive industry in Japan. On your left is the digital optimization. When we provide necessary engineering performance together with the styling or shape preference to meet both engineers and stylist requirement, multi-objective optimization coupled with high precision simulation is automatically executed. Then AI proposes some candidate styles, satisfying both engineers and stylists. On your right is the so-called digital twins. Here, providing on-road driving and surrounding environmental data in physical space. Many high-fidelity aerodynamic simulations coupled with the vehicle's motions and virtual driver's reactions are executed simultaneously in cyberspace. The AI suggests best driving operation depending on the driving conditions. It is no doubt that a supercomputer Fugaku, consisting of about 160,000 many-core CPUs, is going to be the key hardware to support this innovative digital engineering in the Society 5.0. In fact, Fugaku earned the quadruple crown top 500, HPCG, HPCLI, and Graph 500 for fourth consecutive terms at SC21 last autumn, showing its very high computing performance, not only for the conventional scientific simulations, but also for AI algorithms. Then what sort of software should be developed to realize such digital engineering? Firstly, we have to deal with a huge number of simulations at very high speed, including both pre and post processing. Secondly, simulations should be not only high precision, but also tailor-made to realize real digital twin by precisely reproducing each product's shape and considering enormous real-world conditions. Unfortunately, a current engineering CFD framework based on the unstructured mesh system does not meet these requirements from two viewpoints. First of all, as shown in the left, a huge amount of workload is required for the pre-processing, as shown in the pie chart. This figure shows the turnaround time for conventional vehicle aerodynamic CFD in industry in hours. Typically, 8 times a longer time is necessary for the pre-processing compared with the simulation time itself. This is because of the data cleaning required to make a watertight surface for the unstructured mesh system. It also should be noted that this data cleaning time increases exponentially as the surface resolution becomes higher. Secondly, as shown in the right, unstructured data fundamentally have difficulty in tuning on the new hardware architecture because of the irregular memory access. There are various ways to improve calculation efficiently by serializing data access or utilize cache reusability, but it tends to be memory access bounding. In our team, we are also developing and support the unstructured CFD framework called front flow rate. After some tuning of the unstructured software on Fugaku, still its single node performance is less than 3%, and its parallel performance in weak scaling is about 40% on only 512 nodes. From these results, we can say that there are still many challenges ahead for this framework. So we fundamentally changed the data structures from the unstructured to the structured grid, considering its application to HPC on massively parallel environment. Here we adopted a hierarchically Cartesian grid system. The basic data structure is similar to that used in adaptive mesh refinement, having two fixed levels of self-divided spatial domains. The computational space is first divided into cubes, which is evenly divided into 8 cubes as higher spatial resolution is required. Each cube is consisted with numerical cells, typically 16 by 16 by 60 being assigned in our simulation. Since each cube is composed of the same number of cells, it is easy to evenly distribute the computational load to each process. So it is advantageous for achieving a high degree of parallelizations. The interface of each cube is discontinuous between adjacent cubes, so it is necessary to exchange data between cubes in Hello space. The communications and the calculations overlapping technique is partially applied for data exchange, though I don't mention about the details today. The software based on this data structure is called Cube, having been developed in our team since 2012 as a complex unified simulation framework on massively parallel environment. In this framework, we solve multiple partial differential equations on the unified data structure, as I talked before. In addition, unified continuum mechanics equations are adapted for both fluid and structural motions. Thus, Cube is very effective against the strongly coupled fluid structure interaction problem, which is usually difficult to achieve high performance on massive parallel simulations when we solve fluid and structure motions separately. Cube already has many achievements on the flagship supercomputers like K and Fugaku. On your left is the direct feedback noise predictions emitted from a very small gap of a road vehicle, which is generated from a real vehicle CAD data. On the middle is combusting internal engine simulations, including pistons and valve motions and chemical reaction. On the right is ski jumping simulations of the gold medalists of the last Winter Olympics and its comparisons with other jumpers by realizing a whole body pose change from the takeoff to landing and explaining why his jumping is superior to the other jumpers. Regarding the tuning on the new hardware architecture, we could achieve a good performance on Fugaku by Cube as expected. As you may know, Fugaku's node consists of 4 core memory groups, and each group has 12 arithmetic cores. Thus, we use hybrid parallelizations among 48 cores in a single node, with OpenMP inside the core memory group and MPI among the core memory groups. So far, Cube has already achieved about 6.7% against the peak, which is quite higher than the conventional CFD simulation softwares based on the unstructured mesh system, and is 2.4 times faster against the Xeon Phi system. But we still have room to improve room for improvement by memory access serialization, loop collapse, and loop fissions, and array dimension exchange. And our estimated performance after these optimizations will be improved to be about 9%. Situation is much better for parallel performance. In this case, even for the real vehicle aerodynamic simulations, we could achieve the scaling of 74.11% up to 51,200 nodes, utilizing about 28 million numerical cells. Then we can realize the world's largest vehicle aerodynamic simulations on the tens of billion meshes, as shown here. By these simulations, we can evaluate the aerodynamic drag in the cyberspace within the errors almost comparable to wind tunnel measurements in the physical space. However, I would like to note that such one-shot simulation is not very popular in industry. From a cost effectiveness perspective. In fact, they are seeking for more sophisticated or the smart ways of utilizing HPC resources for industrial design. Then what should we do for that? That is to significantly reduce the time for mesh generations. I will talk about this point next. The important thing here is adopting structured or the fixed block mesh itself is a disadvantage for the solid wall treatment in the CFD simulations. In this framework, we take advantage of this shortcoming by adopting the immersed boundary method, or so-called IBM, to reproduce solid surface. Still, there is a problem of accuracy near the wall remaining in our simulations. The advantage of our improved immersed boundary method is its very fast mesh generations without modification of original digital CAD data. Regarding the immersed boundary method, so far, most of the existing methods can be categorized into two main streams. One is an original Peskin type, and the other is methods type. Anyway, both types require identification of solid and fluid part in the numerical cell. We have enhanced these methods by adopting the idea of dummy cells for a wall, including cells. It enables us to specify solid cell free arbitrarily in the virtual space. Then even the wall has zero thickness or gaps or overlaps. It can be modeled without any restrictions of the geometrical topology. By this novel immersed boundary method, we could speed up the pre-processing, including CAD cleanup, by 100 to 1,000 times faster than conventional unstructured CFD. Hereafter, we would like to introduce some of the Hereafter, we would like to introduce some of our achievements using this framework on the Fugaku. The first one is a multi-objective optimization of road vehicle shape utilizing a genetic algorithm called Cheetah, developed at JAXA, Japan. Here, we set up 4 objective functions relating to crosswind stability and fuel consumption rate. The aerodynamic performance of each vehicle shape was evaluated by the high-precision CFD simulations on Fugaku, and the entire optimization process was executed fully automatically. The idea is that we developed a surrogate model by AI technique, developed by the AI technique utilizing the CFD results as a training data obtained at the earlier stage of optimizations. By replacing a part of the performance evaluations with this surrogate model, we have succeeded in reducing costs while ensuring the optimization accurately. These two figures in the bottom left indicate the comparisons of the case. Whole process is conducted by simulations with mixing of a simulation and surrogate model. 2 typical vehicle shapes obtained by these optimizations are indicated here on your right. Above is the highest crosswind stability car, and below is the lowest emission car, having the different shape of us, especially at the rear end. The second example is a digital twin simulations realized by coupling the vehicle aerodynamic simulations and the vehicle's multi-body simulations, reproducing a body's 6 degrees of freedom motions as well as a suspension system. The aim of this simulation is to evaluate the drivability of a vehicle. For the drivability evaluations, very small change in the shape have a great effect on the driver's sense. Thus, the shape of the model must be reproduced as faithfully as possible, as shown here. These 2 animations reproduce the lane change maneuvering without and with atmospheric turbulence, and obtained steering input and vehicle's pose change are shown in the figures. In the current development process of road vehicle industries, this drivability evaluation is possible only in the final process of development, where a prototype vehicle can be made. While once this simulation system is implemented on the real development process in industry, they can evaluate such on-road performance at very initial stage of the development. We believe that optimizing various engineering performance upstream of the design and development process will bring innovations to the manufacturing process. CUBE's very first mesh generation has shown great power in responding to the COVID-19 pandemic. The pandemic occurred early 2020 when we were tuning the cube on Fugaku. We soon noticed that our simulation module for the internal combustion engines and fuel injection model implemented on the cube can be utilized to simulate the droplet and aerosol dispersions for the infection risk evaluations of COVID-19. The innovative point here is not only to treat the risk of infection at the face-to-face level, but also to focus on the indoor space where multiple people are staying. I do not talk about this in detail here, but for these evaluations, we have to realize the digital transformations of the airborne infection risk assessment in many indoor environments, like inside the public transportations or the public areas as shown here. This figure indicates the number of daily positives of COVID-19 in Japan, together with some of our simulation results. For these 20 months, we have treated over 50 social infection scenes and conducted over 1,000 cases for the risk evaluations and the proposal of countermeasures. We can say that this is achieved only by CUBE, which has very fast mesh generation functions and is fully tuned on Fugaku, together with the detailed physical model of droplet evaporations and attachment on the wall, solid wall implemented. With this achievement, we could win the ACM Golden Bell Prize, a special prize for COVID-19 research at SC21. In the award, Professor Mark Parsons, chair of the prize, said, this information helped guide decisions in areas including requirements for face masks and social distancing, as well as whether certain public facilities and private businesses should be closed. Currently, we are now applying this simulation framework to our industrial targets. Four industrial targets. From left, aerodynamics, urban building, indoor environment, and the gas turbines. The project is to advocate the innovative digital design supported by high-performance computing system for industrial applications. This project is supported by the Ministry of Education in Japan as a program for promoting researches on the supercomputer Fugaku. Each subtask is carried out under strong inter-industry academia collaboration, shown here in each specific industrial realm. The smart design will be realized by coupling high-performance simulation, which is also coupled with data science on the high-end supercomputer environment. In this regard, RCCS has strengths and support all these four subtasks. Here, I think I'm running out of my time, so I would like to introduce task A and task C somehow more in detail as an extension of the topic introduced earlier. At subtask A, we are extending the framework of the multi-objective optimizations introduced earlier by coupling the stylist design space to the ordinal engineering design space. It is well known in automotive industry that a simple shape optimization based on only the engineering perspective, like aerodynamic drag or lift, does not work in the real vehicle development because a stylist shape proposal always takes priority. Thus, we are trying to consider stylist design space, which is coupled with a usual engineer's design space to satisfy both the stylists and engineers demanding. Of course, these multipurpose optimizations drastically increase the design parameters and objective functions. Thus, HPC resources are indispensable. In these optimizations, as I mentioned earlier, not only the HPC simulation to evaluate its aerodynamic performance, but also surrogate model or reduction models developed by machine learning techniques are utilized to reduce optimization costs as much as possible. Subtask C is aiming to the smart indoor environment design, robust for the infectious diseases like COVID-19. This is the extension of our current COVID-19 project. As you may notice, our droplet dispersion simulation only predicts the transmissions of droplets emitted from the infected persons and how much droplets are inhaled by the person at risk. After that, we adopt a very rough probability model based on the rough epidemiological assumptions to predict the infection risk. This one, sorry. As you may notice, this is a sort of the unified simulations. That because we use, as I mentioned, we use a very rough epidemic models to make our predictions more reliable. In the Subtask C, we are integrating our simulations with a more microscopic risk assessment based on the bioregulation model, together with more precise human body and respiratory tract numerical models. In addition, we are currently measuring the droplet size distributions and flow rate of human breathing in the physical space, currently I mean, and impose them as boundary conditions. It means so far, we do not have any information of how many viruses included in each droplet. To include such information in each droplet size in our simulations, we have to go back to the mechanism of how droplets and aerosol are generated in the respiratory tract and overall cavity of infected person. So we are now trying to combine these different types of simulations at different scales and try to conduct the sort of the unified evaluations of infection risk. And this is one of the examples of our current simulations of host cell dynamics coupled with a numerical respiratory tract. As shown in the left, virus-laden particles that reach the breathing zone are transported from the neurus into the upper airway and partly deposited on the inner wall, and some of them transported to the lower respiratory tract. As shown in the upper middle figure, there is a clear correlation between the airway depositions and the particle size, and fine droplets of 100 nanometer or less are well deposited in the airway wall due to the effect of a Brownian diffusion. Similarly, particles larger than 1 micrometer diameter deposit well in the upper airway due to the gravitational settling effect. The deposited virus-laden particles of mucus are transported in the directions of the larynx by mucociliary motions, as shown below middle. At the same time, the virus infects the host cell and begins to replicate. The time series of the change in number of susceptible cells, infected cells, and viral RNA copies are obtained by solving the host cell dynamics model, as shown in the right equations. By solving these equations, as shown in the above right, in these analytical conditions, assuming COVID-19 infection, 2 days after the inhalations of virus-laden particles, our simulation predicts that the virus concentrations exceed the detection limit of a PCR test and peaked 5 days later. Okay, finally, I'd like to summarize my talk. I have introduced the example of smart design to be realized in industrial world in the Society 5.0 era by utilizing Fugaku as the hardware and Cube as the software. The key is how we can expand the possibility of simulation, current simulation, which is used in the industries currently as a very conservatively as an alternative to experiments in the physical space by combining, by combining the data science and utilize AI technologies, we can expand its possibility. Unfortunately, current conventional or commercial CFD package is not suitable for that purpose, because of the requirement of a substantial amount of the pre-processing for the dirty CAD data, as well as the difficulty in optimizations on the new hardware architecture. And new simulation framework, including the data structures like Cube introduced today, is indispensable to fully utilize the HPC resources in the industrial world. Thank you very much for your attention.